All right, guys. Um, I have a very interesting. That number's gonna come into play here soon. I didn't mean to show it to you though, but I have a very interesting thing that I want to do here, and it's something that I really like the idea of. It's something that I think relates to some tools that can be used in artificial intelligence and things like that. And it's very mathematical in some senses, but it's also very fun. And there's a website that has these little Turing machines, and I actually want to show you the website along with this video. I don't want to just show the video. So here's a website. I'm going to put a link to it in the description. But here's a little Turing machine that's drawing pixels here using just, some JavaScript and whatnot on a website. Now, if I increase the speed, notice that this little guy actually draws some really interesting stuff. I mean, look at this. It looks like there's little triangles, some kind of just repeating pattern here. And that's really cool, like with these triangles and with these little graph things or whatnot. And I just really liked that. I thought that was really cool. You can randomly generate, see there's number of states, number of symbols. You can randomly, generate new ones. And it's just really, really cool. And I made a video like this to music before in the past. And then I also, just for fun, I kind of did some coding on my own. So this I kind of coded this stuff on my own right here. Now it's updating really slowly because the way I update it is I process some of it and then kind of did a slower version of copying this section of the screen. But what I'm doing here is I'm running I think it's three Turing machines, all sharing the same memory. So they each are independent Turing machines with different memory of their states and symbols, but with the same shared screen pixel symbols. So they all share whatever pixels are on the screen, and you get even more patterns, I guess, possible, because now that you have an interaction between different kind of machines making patterns with each other. And I just thought that was really fun, to be able to make something like that. So let's just load another one right here. And I think it's going even slower because I'm trying to both record and process some videos at the same time. But notice, like, this pattern that it makes right here, is pretty interesting. I'm only using 4 colors and 4 states for each of the machines, but it just so it's just a fun thing to mess around with. So anyway, let's get back to the calculator programming. But so let's say you're some little guy here and you want to explore all possible things that you can do, but you want to save memory for what you're doing and kind of print things as you go. And so let's say you have different options. So you could move right, you could move up, you could move down, or you could move left. But then you could sort of color, or I guess in this case, print a different character wherever you go. So let's say you want to move to the right here, and then you print behind, a star. But then after you moved right, you kind of thought, well, if the last thing I did was move right from a space, where I printed a star, and then I moved onto an empty space, then maybe I want to move down and, leave behind a period or something like that. And maybe after I moved down, maybe I want to move back up again. And if I hit a space, I'll do something, but if I hit a period, I might do something else. So you move up and you realize, oh, I hit a period. Oh, and by the way, I was supposed to print a star when I moved up, just because, you know, that's what he decided to do for that type of decision making. So maybe he has a few different states. Maybe he only has like 3 different states where he decides what he's going to do based on what he sees and what state he's in. And the things that he's deciding that he's going to do is either move up, down, left, or right, and then what to print, and then also what state he's going to be in. So is he going to move from state 1 to state 2? Is he going to move from state 1 to state 3? Is he going to move from state 1 and just stay in state 1 if he's, you know, on a blank space or something like that? Or if he's, maybe he only goes to state 3 if he hits a dot or something. So I'm just going to show you guys. These can print. Sometimes they just print this messy garbage, but sometimes they make beautiful patterns. It's crazy. And but I'm just going to show you the numbers here, so you guys might be a little mind blown here. So I kind of drew up this math a little bit to try to figure out how many different machines we can build here. How many different of these guys we could possibly make. And so I just assumed, you know, let's just say we only had, you know, 3 states. That's it, just 3 states. And then let's assume that we only had 3 colors. So we have color A, B, and C. So let's say we have spaces, dots, and stars. And that's it. And then we just move up, down, left, and right. And we just kind of pick those randomly. And we say, okay, well, our machine is going to be defined by this table right here. So whatever state we're in, we're going to decide whether we're going to move up, down, left, or right based on what color we've seen. We move that direction, and then we decide which state we're going to go to and what color we're going to leave behind. So here, if we see a B, we're going to leave behind C. We're going to move left, and then we're going to go to state 3. So now we move left. We see some other color. When we move left, let's say we saw color A. We're in state 3, so we do this right here. We move to the right, we leave behind a B, and we go to state number 2. So we go back here again. So this kind of defines what your little machine will do, and then he kind of uses the screen for memory. Now what's funny is this is such a simple set of things. I mean, it looks like he's only got 12, you know, not even 12, 9 instructions, right? That's it. But each instruction can be one of 4 possible directions. It can be one of 3 possible colors and one of 3 possible states compared to all the rest of them, right? So how many different machines do we really have? How many different combinations like this do we even have total? Well, if you want to count in like binary, how, you know, every time you add a bit, you have to multiply it by how many bits there are. So if there's 2 possible bits, 0 or 1, you have to take that 2 and raise it to whatever power. So this would be 2 to the 9th power if these were just zeros and ones. But they're not. They have 4 times 3 times 3. So it's actually 12 to the 9th power. Which, by the way, that is a really, really big number. That has like 14 base 10 digits. To write out that number, I would have to have 14 digits long. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I mean, that's a big number. So I'm not going to loop through them. I'm going to just like generate random ones because it's too hard to search through all of that many using this method. If I really wanted to search through these, I would both use a faster machine and optimize it. And if I really, really, really wanted to optimize things and use faster and faster machines, I would start doing things in parallel. I would research into combinatorics and sort of, if I did a really good job at both of those things, then I would eventually try to maybe use like supercomputers and things like that to help assist doing that. But as far as just, you know, that number there, I mean, that's a big number. So let's go ahead and see if we can actually make one of these Turing machines. So let's actually call it Turing, just because, you know, and I like Alan Turing. He was really smart. So I'm wondering if we should use 3 matrices for this. I'm wondering if we should use 3 matrices for this. So we could say 3, 3, store as the dimensions of matrix A, right? Now you guys might be wondering, why are you using 3 matrices? I saw 1 table. Well, you saw 1 table, but each of the items in the table had 3 parts to it. And the problem that I'm trying to solve is, how do we clearly identify, I mean, I could probably represent each of the possibilities with 1 number, but that would be hard. It would be hard to understand the code. So instead, let's go ahead and just say that A is just going to store the directions that we want to move. B is just going to store the color that we're going to print, and C is going to store the new state that we're going to go to next. You get what I'm saying? So yeah. So what I'm going to do is I'm just going to create a random one. So for A is 1, 2, 3, and for B is 1 to 3, and then I'll end both of those so that they're balanced. I'm going to think very carefully about what I'm going to store in these. So if A is going to be the direction, then I need a random integer from 1 to 4, because I'm going to try to move every time. I don't want to stay in the same spot, because that, I don't know, it just kind of slows things down. I want to see things printed to the screen, so I'm going to sort of force that we don't have the possibility of just staying in the same spot. We want to move around. In fact, I think even Turing machines that are, you know, used for math proofs and binary sort of do move at every position. So we're going to randomly store a direction in each of the positions in the direction matrix. And what's nice about this is we don't have to worry about, you know, since it's 3, 3, we don't have to worry about we don't have to worry about the matrix kind of not being square. So whoops. So there's 3 colors and there's 3 states, and I think that's okay. So but there is 4 directions. So for the rest of these, we're going to store a random direction and a random 1 of 3 random. Am I explaining this right? 1 of 3 possible colors and 1 of 3 possible states. Right? So if we run this, let's just run it. Okay, it says done. So here are all our possible directions. Okay. Here are all our possible colors. And here are all our possible states that we go to. Of course, next time we run it, it'll be changed again, but that's okay. So now I want to start us off. Usually I tend to always start off at 4 and 4 for the x and y coordinate. But now we want to sort of I guess we can make it so that we sort of make an infinite loop, but next time we do it, what I can do is I can add another loop outside of it, and if I hit a key, then it will reset to a new machine, I guess. We could do it that way too. But let's not do that yet. So what we'll do is we have to actually code the back logic, basically the machine that runs the machine, in order for this to even work. So the first thing that we do is, well, we're going to say that we're starting in state 1. So we need a state. Okay. So, and then we need a color. Don't we? Or do we not need a color? Well, we have coordinates. We have coordinates. Oh! I totally forgot about something. So 0... So hold on a second. So 8, 16 store as dimensions of matrix D, right? Because we need to store our pixels, our screen. Fill 0 matrix D. I can't remember if you probably put the matrix first. And we don't put 0, we put 1s, I think. So our current state tells us what to do, right? So we don't want to just say output. What we want to do is we want to get our color based on our state. Right? So our color is B. So matrix B. And then we give it our state. Let's see here. So Y okay. Let's think about this for a second. So Y is going to be our different states. So matrix B S, comma, and then C store as no. Something's not right. We're going to output store into matrix A, no, matrix D, yx. Okay. No, but we got to store that into a new C, I think. So C is just going to be a temporary variable because we have to use it multiple times, I think. So, because first of all, we have to get our color of where we are. So matrix D of yx, that tells us our current color, right? And based on our color, we take that and our state to find the new color, which is, we're just going to store that into C. Then we got to store that and we have to output it because we have to see what's going on. Right? So if C equals 1, then we're going to store just a space into string 1. If C equals 2, we're going to store a star into string 1. And if C equals 3, then we're going to store a dot into string 1. And then we're just going to print string 1 at our current coordinates before we move. So before we move, we're going to print them. Okay, now is where we look up our... Here, I noticed there's a problem here. We can't use C up here. We have to save it. I lied. Well, let me think here for a second. So what's funny is I'm wondering if this would do the same thing, because we could store the movement that we take, you know, based on the color that we print, or we could base it on the color that we... No, but that wouldn't even make sense, I don't think. It should be based on the color that we see. I don't know if that would really be the same set of like possibilities, if you will. But I'm trying to think here. Because B of ST, I'm sorry, not B of ST, ST in general is where we need to get our information. So we need B of ST, but we also need A of ST to get our direction. And C of ST gives us our new state. Right? And when I do that, notice that S is changing. So we can't change our state until after we've used it. But A of ST is, remember, A is our direction. So we can store that into, I guess, D for direction. Okay, so T is a temporary color variable that we're using to remember what color we landed on, so that we know our state and then color memory that we're using to decide what we need to do. And then everything is based on that. So we're deciding what color we're going to store in that spot. And then we're going to, and then we don't access that anymore. So once we get that color, we can overwrite it, and we can just use our table. We should never be writing to A, B, or C, which we aren't. We're just getting from them. Because remember, those are just our static definition of our machine. It doesn't change. It's not like a machine that keeps reprogramming itself. It's programming the background. That's what it's doing. So it's just like a behind the scenes logic, which we can update, but we don't want it to just update all the time, randomly changing all the time, because it might have an interesting pattern to it. So we have the direction. So here we say, like, if D equals 1, x plus 1 stores x or something. If D equals 2, x minus 1 stores x, I guess. If D equals 3, y plus 1 stores y. And if D equals 4, y minus 1 stores y. Okay, and then of course we always have to check if we want it to wrap around kind of like a, not a Mobius strip, what is it? A torus. If x equals 17, 1 stores x. If x equals 0, 16 stores x. If y equals 9, 1 stores y. If y equals 0, 8 stores y. Okay, so we updated the coordinates, right? We still have t and s, and here we update s. And the next thing we do, since we moved, is we update the t based on our movement. Okay. So I've never ran this before. This is the first time I've ever made a random Turing machine on my laptop. Or on my laptop. This is the first time. That is so cool. It's going to the left and then it's stair-stepping down. That is so cool. Now it's going down because it's hitting the stars. So let's see what happens when it runs out of the stars. Maybe it'll do something different when it runs out. Nope. Okay, let's run it again. So it's going right. Okay, so it goes right until it hits dots, apparently. So that's so cool. And I didn't clear the screen. So it's like whatever was left behind was left behind. Okay, now it's like making patterns to the right. And remember, guys, I just made another Turing machine. So whatever pattern you see here, look, it's like it's making the flag or something. Whatever patterns you see here, it's coming from machine number I guess number 2. We just randomly made another machine. Or if you want to call it, you could call it a program. It's like a random program. I could also initialize the screen to be random to encourage difference so that it's not so boring what we see. Because right now it's like the screen starts off with one pattern and then our Turing machine kind of has to go through and like overwrite the whole pattern. I could increase the number of states and the number of quote-unquote, I guess, colors, if you want to call them that. Just to make it more sophisticated. So let's go ahead and do that. Let's actually do that. So let's go to Turing machine and let's actually increase it. So it's going to be insane, the number of like possible things we have here. So we have 4 states and 4 colors and then 4 directions. So it's like insane because the number of them is what, 4 times 4 times 4 to the 4 times 4 power. Like, so 64 to the 16th power, I guess, number of possible things. And so for so if c equals 4, I guess we'll put like a minus sign or something. Store as string 1. Yeah. And then I want to make sure that we don't skip out. So yeah, nothing else needs to change. It should just work. I could make it so that we randomly assign to this. Oh my goodness, this is so cool. Okay, let's restart it again. What is it doing? It's going down and then left and then up and then down. Okay. This is so weird because you never know when it's like what it's going to draw. And if you guys ever seen the computer version of this, it is amazing. I actually made a video called LinkedIn's Ant. I think I referred it to LinkedIn's Ant, and I made a whole bunch of these machines from a website that was designed to use these to make really cool patterns. And you could just make random, and it would update it update the screen so fast you couldn't even see the iterator. You would just see a pattern. So you would either see something that looks like water or static or some cool like, triangle patterns, things like that. And I put it all to music. But this is cool because I'm doing it on my calculator, and not just on the calculator, but in a TI Basic, which is really inefficient. And then on top of that, I'm storing string values and like using matrices, which is really, really slow, but it's still working, still running. Apparently it's trying to teach me Morse code. So let's run another one. Okay, this one apparently likes to just move to the right and print blank. Let's do another one. There we go. I almost wish there was a way to... Maybe there's like a way to... Maybe I should put the whole thing in a loop. And... I don't know, like if it gets stuck or something like that, if there's a way to hash it to know when to change. Either that, or I could loop it for like, you know, 100 or something. But then I could do a get key. Okay, that's kind of cool. It's making lines and stuff. Okay. And if only there was a way I could, like, you know, oh man, there's so many possibilities. I just think these are so cool because when it comes to like genetic algorithms, like combining them, like imagine just combining like these tables to generate things that you might want, like interesting tables. You might try to find ways to combine them and just interact with them, like combine them with genetic algorithms, combine them with neural network algorithms, and just see if you can make stuff, just generate stuff, and try to come up with algorithms that are good at combining algorithms and things like that. It's just really cool because I don't know what these machines, you know, really capable of it, except for, you know, computational things, and that's about it. I mean, they're not even using random to their advantage. They're just following a strict table. So they're just finite state machines with a memory of a torus shape, you know. But they can do things, theoretically. They can do things like, I mean, you can program Turing machines to, like, you know, add numbers and things like that if you really wanted to. It might be a silly encoding of the numbers, but I mean, that's how a Turing machine is used in math. Like if it couldn't do all those things, it wouldn't be so important in mathematics. But Turing machines and lambda calculus, those are important because they're used as a basis for computation. There's no known sort of thing outside of computation that computer algorithms can do that you can't do with the Turing machine. That's what's cool about them. So right now, I don't know what it's doing. This one looks pretty cool. I like the pattern that it's making. Or I guess the pattern that it's living, if you will. I can't really see what it's making, but it just looks cool the way it's moving around. It almost looks random the way it's moving around, but it's not random. It's following some pattern here, but it's just that the screen is so messy that I can't really tell what it's doing. I think when it hits a star on some states, it's moving down. I'm not really sure. It's kind of weird. But remember, like, this is a complex machine already, even though because it's not just one state. It's not just, oh, every time it hits a dot, it moves left or something. It has 4 different possible states, and some states might only get reached under interesting circumstances, like if it hit a line and it was in state 3, and then it hits another line, then maybe that's the chance that it has to go to state 4. And then state 4 might do something, you know, throw it off of its pattern or something. So it's kind of cool because it's like, you know, randomly generated thing. I wish I could, you know, somehow check all, you know, 10 to the 50th or however many there are of these things, to see if there's any of them in there that are really interesting, that are really cool, that do things. So this one, I don't know, it keeps going. I like it. That one's really cool. That's kind of fun. Let's just do another one just to change things up. Looks like it's going left lines and then left asterisks. Left lines and then left asterisks. Oh man. I wish I didn't have to wait for it to fill out the whole screen. Part of me wants to skip to another one, but part of me wants to see if there's more to this one or if it's just going to be stuck trying to go down. I wonder if there's a way to combinatorically, remove all the Turing machines that you can't reach all the states or something like that. Like if there's a state you can't reach. Oh, did you see that? It went up. That's interesting. Okay. So this one is capable of doing more than just printing lines and then printing stars, but I think once it goes up, I bet you it's gonna do it again. Although it is in a different state. So as soon as it starts going left again, I'm gonna be mad and I'm gonna say, okay, let's move on. It's going up. Well, I don't know. Maybe it's stuck in this state now. So I think the idea of each state just at least being able to refer to the other states is important. There's some cycle, basically. If there's not a cycle, like if there's a sync state, which means like once you get to the state, there's no going out or something. Or if there's a source state, which means once you leave the state, there's no coming back, then then you don't have a good Turing machine. Then it's not considered dynamic anymore. It's part of it is static. Part of it is just to initialize itself, and then the rest is what goes on forever. So this one is getting boring. Let's try this again. Okay. Ooh, what is it doing? We can make two of them too. That's the cool thing. Is you don't just have to have one of these things. You can make them like fight. And one of them is like trying to print everything as dots, and the other one's trying to change all the dots to minuses, and you can make Turing machines that try to kind of do different things together, and fight each other, and they have different. Point is they have different cursors, so it's kind of like one machine but with two points of interaction. Maybe they could even you could even do something like that where you have 2 points of interaction, but it's the same machine. So based on what the 2 points see as far as colors, there's a combination. So you could say if point A sees a star and point B sees a dot, do, this thing or whatever. And you could make it work that way. That would be really cool. I would love to see if somebody could make some really interesting patterns from that, because then things would get really interesting. Then you wouldn't just have you'd probably be able to draw more things, because of the fact that drawing on a torus is kind of limited when your machine only can move up and down, because it sort of has to fill everything out every time it wants to draw anything that has some kind of base pattern to it. And I think that's a limitation. I think it's a limitation to have one cursor. So to have multiple cursors, I think that I want to try that. I want to program that in JavaScript sometime, actually. I think that's a new programming project that I have to do now. This is so cool. It's just getting me thinking, and I love it. I love it. It's just so cool. It's just fun. It's just fun to like mess around with this stuff. And that's how it should be. Don't ever think that you have to be, you know, super expert at, you know, any of these things, because it's about having fun. If you really like, if you're really gonna be a, a coding person, you can't let what other people, you can't let other people define you based on what they think, because I have proven that people are wrong a lot of times. And I'm saying this as a mathematician who likes to prove things, and I'm not just saying this as like this was an opinion. I'm saying I've actually proven people wrong. Um, and seen people just completely believe the wrong thing. Like they'll think that you might not know of a certain subject. I've been in situations where people just pull out of a project. They pull out of a strategy that you have. They pull out of they pull out of believing in someone who really knows their stuff, but it just doesn't look what they what they believe in. They believe in money, they believe in professionalism, they believe in all these things that look good. But you can have a solid mathematically true thing and you can say, I know X is going to happen. And it could just be a pure mathematical statement. And you could be 100% sure of that statement. And guess what? They won't believe that statement. And you can bet your butt you can't depend on everyone to know that. This happened to me multiple times. This happened to me on a quiz I was taking for a computer science professor, and you know, he had to come back and say he ran a simulation to find out that I was right. Okay, I was playing a video game with people, and they didn't believe in the strategy, and they quit, you know, in the middle of the game. And then my strategy was so good, I still beat the other team without my teammates. And it was just some simple math. So have fun. I mean, the guy who made Minecraft, you know what he said? He said it's about like having fun. When his company grew, it frustrated him. He sold it to Microsoft, but now he has billions of dollars and he can go make another game. He doesn't have to be restricted. Like, sure, he couldn't really handle that company very well, but he made the game in the first place because, and this is a soft idea. This isn't a very hard idea that I'm explaining, but it goes along the same point. The type of person who made that type of game was not someone who is strategizing to make a huge popular game. He wasn't. I mean, his game looks silly to most people. But the point is he was having fun anyway. He was already recording all these videos and making all these little 2D games just for fun when he made that game. Let's run it again. Here we go. I do not see anything happening. I think it's stuck. Excuse me. This one seems to want... Oh, there we go. It's going up. Man, this is so fun. This is so cool. This is so cool. I wonder if we can make one with two. I want to do that on the computer, though. I don't even want to do that on the... Because doing it on the calculator is one thing. But I want to do this in JavaScript. On the computer, and then I want to show you guys when I do it with like two I'm going to try to do it with like 2 cursors or 3 cursors or something like that, because that's going to be fun. That's going to look really cool. All right, so this has been Tim. It's been fun, and I will see you guys later. Bye.